All right, I thought I'd do some in the 50s. Wanted to get into some of the later sections, so maybe I'll catch up with problems in the 30s and 40s a little later. But I like this one and wanted to do it for you. This is a problem that takes into account the individual collisions of molecules with the wall of the container. In particular, this question's asking us to calculate the pressure with the condition of argon atoms in a container that are hitting a 4.0 square centimeter piece of the wall per second. And they give us the speed of 45,000 centimeters per second. This is going to challenge us for a couple of reasons. We have to be really careful of units, and we have to calculate kind of a couple different pieces to give us the whole. What I mean by that is the pressure is defined as the force per unit area. We're going to have to figure out the force first before we apply it to find the pressure. One little thing about the setup for this question, you might have noticed that in the text they list the collision angle of being not 90 degrees Celsius, a 90 degree angle. Essentially what they mean is just the vector of the speed is hitting at the wall directly. So the entire force is being hit on the wall straight on. It's not hitting at an angle at which you'd have to figure out what component is, let's say, the x direction. But if you look in your text, there's sort of a very elegant derivation of how pressure can be derived from individual collisions. I'll represent some of that here, in which you could think about the force of this system, which is about 1/3 of a mole of atoms, but the force of the system is going to be the force of an individual atom multiplied by how many atoms you have. So force of a single atom times the number of argon atoms is going to give us the force, or the numerator in the pressure expression. From the text, there's a discussion of what the force is of a single atom. Basically, it is the change in the momentum. If you take a look at that, you might recall that you need to account for the directionality of the atom before and after collision, which is why the numerator here is the change in the momentum divided by the time. And then again, we have to multiply by the number of argon atoms. Well, folks, it looks like I never hit start on my recorder here, but I did write out these answers, and I'm a little pressed for time, so I'll just leave this up. Let me narrate these two short problems for you to see how I proceeded. 2.54 illustrates for us a calculation that uses the average translational energy of a molecule. So for any atom or molecule, the average translational energy, which is represented by this designation here, is 3/2 times the Boltzmann constant times the temperature in Kelvin. The Boltzmann constant, you could look that up very easily, and as you might expect, the translational energy for an individual molecule is going to be really, really small, 10 to the minus 21st joules here. If you realize that the gas constant is just simply Avogadro's number times the Boltzmann constant, you can convert this for 1 mole's worth of nitrogen. And it's going to be obviously a substantially larger number, although not a tremendous amount of energy. Nitrogen molecules just bouncing around room temperature don't have tons and tons of energy inside them. We also did some equations that looked at the different ways to look at average speeds in a distribution. If you recall, the root mean squared speed was important in these systems because it tells you what the average speed of a molecule is that has the average kinetic energy. And so I've reproduced that equation here. The root mean squared speed for any sample is the square root of 3 times r times t over the molar mass. Because we're in the kind of energy realm, you're going to be using the 8.314 version of the gas constant. I recommend that you redo this problem writing out the individual units for joules. Remember, kilograms, meters squared over second squared, just so you see how everything cancels. Anyway, we were given the speed of this sample of methane, and if you churn through, you see that the temperature is 460 Kelvin. So a substantially warm environment for this kind of speed. Let's take a look at 2.58 with another treatment of root mean squared speed. This is a nice question. You have to think a little bit. It's asking us to calculate the temperature when helium atoms have the same root mean squared speed as nitrogen at 25 degrees Celsius. So comparatively, the nitrogen molecules are much heavier, so you would expect that their speed would be slower if both samples were at the same temperature. But what they're asking us to do is to find the temperature at which helium will have exactly the same speed. So that's why I set this up the way I did. I set up the root mean squared speed for helium on the left and the root mean squared speed for nitrogen on the right. Both of these are going to differ in just the temperature and the molar mass, so we could eliminate the 3 and the r terms when we solve for T. So that's what I've done here. I took the temperature of the helium over its molar mass in kilograms per mole and equated it to the square root of the temperature of the nitrogen over its molar mass in kilograms per mole. Once you do that, you're going to end up solving for the temperature, which gives 42.5 Kelvin. A very, very cold temperature is going to slow down the helium atoms enough that they're the same speed as the nitrogen at 25 degrees Celsius. So that should make sense to you from a conceptual point of view. I'll do some more problems later in the chapter and kind of maybe fill in the rest a little bit later. Bye for now.